Hello everyone and welcome to Math 265 Exam 1 review. Mainly in this review, we'll be covering some important topics that will show up on Exam 1 for Calc 1 course. To introduce myself, I am Sanjana Shah. I am a computer science major and a sophomore at EF School of Engineering, and I am a special programs tutor. At the same time, you can also follow the FSC tutoring page on Instagram and Facebook for further updates on our other lectures. Moving forward, this lecture would mainly set up a list of questions that could turn up and the uh, important concepts up behind them and some sample questions. So some of the skills here for exam 1 would be evaluating limits, as in a question will be given and you need to figure out how do you need to evaluate a limit if you are working with squeeze theorem, is there a direct substitution property, and get to the answer for that limit. Of course, using the squeeze theorem to figure out the answer. Apart from that, there is determining where f of x is continuous, which would be really similar to graphs. We'll be looking for piecewise functions. And apart from that, there will be the limit definition of a derivative. Derivative is something which will mainly be covered in chapter 2 and the mastery exam. But the part where limits and derivatives are linked together to maintain a continuity, no pun intended, is this. So the first part, checking continuity. So whenever you want to try to prove the continuity, a simple basic concept to keep in mind would be to prove that a limit exists when limit of a certain variable tends to another value, such as to prove that limit x tends to a for f of x is equal to L. You need to prove that the left hand limit is equal to the right hand limit. Again, we do not care about what is the value of the limit at a, we just want to know what happens before a and what happens after a. Let's look at an example. Suppose this is your question. The given graph is on the screen and you need to figure out limit of x tends to -1. To figure out limit x tends to -1, whether it exists or not and what it is, you need to figure out individually for x tends to -1 from the left and x tends to -1 from the right. For example, for this part, we'll go and look at the graph and point to -1, which is at this point. And when it comes to -1 and approaching it from the left, which is shown by the negative sign, you can move from the left-hand side towards -1. And as you move towards -1, you can see that the y value at this point is 0. So limit of x tends to -1 from the left is 0. When it comes to the limit of x tends to -1 from the right, so at that point we'll approach it from this end and move towards the right towards -1. In that case, again, as it approaches -1, the y value turns out to be 0. So here as well, the answer is 0. Now, as you can see, limit at the left hand side is equal to the limit at the right hand side, which means that limit for x tends to -1 in general is also 0. On the other hand, we'll look at the second example where it shows limit x tends to 1. Again, we'll approach from the left-hand side and the right-hand side. When you approach from the left-hand side towards -1, you'll see that the y value tends to -2. -1, -2. So you know that the answer here is -2. However, when we approach it from the right-hand side, as in from this end, we can see that the value of y is actually -1. So the answer for the right hand limit is -1. Now the left hand limit is not equal to the right hand limit. This implies that in this case, the limit for +1 in general does not exist. I'll clear the annotations. We'll move to the next question. Now, when it comes to calculating limits, the main skill lies in the fact in understanding what property do you need to use. Can you use direct substitution? Direct substitution is just putting in numbers and calculating the result of the function. Or do you need to change the function? Do you need to use algebraic identities to change its form? Do you need to use trig formulas to maybe convert sine and cos into cot and tan, maybe? Or if the square root is involved, sometimes you might need to rationalize the problem. Let's just look at the examples. For example, for simple question 1, we have limit x tends to 5 and the given function is 2x squared minus 3x plus 4. Now, what property can we use here? To understand how to begin, it's always a good idea to put the value that is given as x tends to into the function. As in this case, if x tends to 5, you want to begin by putting 5 in the given function. In this case, it would become 2x squared, 5 squared is 25 minus 3 into 5 plus 4, which simplifies to 50 minus 15 plus 4, which is 39. So the answer we get here is not undefined. There is a concrete value for it. So in that case, if we get a concrete value, it means that this number, which here is 5, lies in the domain of f of x. So we plugged 5 into f of x and then we got a finite value. As you can see, once we know that we can apply direct substitution, we'll separate out the limits with each individual term and carry out the limits for that, as in separating them from addition and then from multiplication, and remove and bring the constants outside, as in this case 2 was brought to the outside, 3 was brought to the front, and then calculate the limits. In this case, which is again just putting in the constant values. Which gives us our answer. Next question. Next question involves limit x tends to 1, x squared minus 1, x minus 1 divided by x minus 1. Now again, to figure out how we're going to move forward, we should just put 1 in the domain of the function, which will again go ahead. When I do that, I'll actually get 1 minus 1, the whole thing, divided by 1 minus 1. Again, as you can see, this turns out to be 0 divided by 0, which basically does not make sense. So that is undefined. Well, when it is undefined, we can clearly say that the given value when it's undefined, we can say that this value does not lie in the domain of the function. When it does not exist in the domain of the function, we have to change the function in a specific way to give us a different formula, which will lead to at least some result for the limit. In this case, as you can see, x square minus 1 is an algebraic identity which we can change into x minus 1 into x plus 1, and there is obviously x minus 1 in the denominator. X minus 1 in the denominator and the numerator would cancel each other out, and then we'll be left with limit x tends to 1, x plus 1. Now, again, we can just put 1 in the domain of the new function, which here is x plus 1. If I put 1 in this function, I get 1 plus 1, which is 2. So obviously it is not undefined. And thus we use number substitution for this part of the question. And that's how we get 2. Consider the next question. Again, I'll try to put 0 in the domain of the function. Just to think quickly, if it's always easier to put the number directly in the denominator, and the denominator turns out to be 0, it's pretty clear that the answer is undefined. As in this case, if I put 0 inside of t, if I put 0 inside of t, I get 0, and any number divided by 0 is undefined. So that part is clear that we will not be using direct substitution theory in this part of the question. So we need to further change the question to give a form where we can actually use substitution theory. In this case, we can always rationalize the function. On doing that, we get these terms where the 9 and 9 cancel each other out, the t square and t square will cancel each other out, and eventually we turn up with this term. Now, if you look carefully, we can actually substitute t in this term. As in, at this point, if I substitute t square with 0, my answer would just be 1 divided by square root of 0 plus 9 plus 3, which becomes 1 divided by 3 plus 3 and that gives us 1 divided by 6. Now, one important concept that comes up again and again is that when limit tends to 0, something happens with sine theta divided by theta, which the scenario is that sine theta divided by theta when limit tends to 0 is actually equal to 1. So if there is a sine theta in the question, maybe just consider it as a hint. Maybe you can use this entire identity to turn that form into 1. However, pay attention where you can use this identity sine theta divided by theta is equal to 1 only when the limit of theta tends to 0. You cannot use it for any other finite value or when it's undefined. Let's look at an example. Suppose this is our sample question. Limit x tends to 0, sine 7x divided by 4x. Now, first of all, let's see if we can express the function differently in sine theta by theta form. In this case, our theta is actually 7x. So, some way or the other, I need to bring 7x to the denominator. In this case, I can just multiply the denominator and the numerator by 7 and 7, and the form turns out to be like this. And do that, this entire part, which has been this part becomes 1, which, as you can see, limit x tends to 0 when the entire thing turns to 1 is 1. If this part is turned to 1, this entire thing again turns to 1. Again, this will also turn to 1, and our final answer would be 7 by 4. Next comes the squeeze theorem. Now, a good way to describe this would be, imagine if I tell you that people older than the age of 12 are called ice creams. People who are younger than 20 are also called ice creams. So what would you call people of age 15? Again, ice creams. That's what we figured, because in the entire scope between 12 and 20, the people are called ice creams. So someone age 15 would also be ice cream. There is a slight correction here. H of x is, for this part, it's actually g of x. So that is the squeeze theorem. If f of x is a function that's less than g, and h of x is a function that's greater than g, and the limit of both the functions comes to the same value, then you also know that g of x will have the same value. Let's look at an example if that will help us out. This is our sample question. Prove that limit x tends to 0, x squared sine 1 by x is equal to 0. Now, one thing that you cannot do here is substitution. Why? Again, if we begin by substituting 0, we'll get x squared, which is again 0, multiplied by sine 1 of x. 1 of 0 tends to undefined. Sine of undefined is again, well, not undefined, it's between 0 to 1, but a limit for that part of the function does not exist. As you can see, we cannot use sine square x tends to 0 sine 1 by x. Instead, what we can use is that the range of sine. Now, we know that the value of sine always lies between -1 and 1. So, even if the theta is 1 by x, the value would be between -1 and 1. Now, if you look carefully, how can we turn this part of the question into something similar to the original question? A good idea would be to multiply it by x squared. Now, it remains the same if I multiply x squared everywhere. And if I multiply x squared everywhere, the inequality would also remain the same. This one would look like negative x squared less than x squared sine 1 by x is less than 1 by x, is less than x squared. Now, while we cannot compute the limits for x squared sine 1 by x, we can actually compute the limits for negative x squared and x squared, both of which actually tend to 0 when you just substitute 0 into x squared. And if the two halves of it turn to 0, the middle part is also 0. Apart from that, we have a question of what to do when the limits tend to infinity, as in x tends to infinity. It talks about questions where, suppose you pay, apologies for that, $1,000 for every credit hour, but more than 15 credit hours, you pay $15,000. So even if I'm taking 19 credit hours, I'm still paying $15,000. If I'm taking 21 credit hours, I'm still paying $15,000. So initially, the price was rising, but when the credit hours rise indefinitely, beyond 15, the price remains the same. In that case, limit when x tends to infinity, price of your tuition fee tends to $15,000. Now, a good concept to remember when we are dealing with limits of infinities would be when limit x tends to infinity, 1 divided by x raised to n would turn out to be 0. And when limit x tends to negative infinity, the same thing comes into play and 1 by x raised to n would again be 0. These two topics are important because often they turn the entire calculation into 0, which would just reduce the number. How to evaluate limits involving infinity? To evaluate limits involving infinity, start by dividing the numerator and the denominator by the highest power that occurs in the denominator. And whenever possible, apply the given formula mentioned before. For example, in this question, the highest power of the variable in the denominator is x squared. So we'll divide the entire function, each term in the function, by x squared. This would turn out the following way, which eventually becomes of this form. Now, if we apply the previous logic of using limit x tends to infinity, 1 by x raised to n is equal to 0, the following terms will become 0. If all these terms become 0, we're eventually just left with 3 by 5. So, final answer is also actually 3 by 5. Let's deal with the idea of the limit definition of a derivative. When it comes to limit definition of derivative, the questions would mainly be concerned with calculating the tangent and calculating velocity. And the limit definition of derivative is f of x, f dash of x, which is also the derivative of the function of x at number a, can be defined as limit h tends to 0, f of a plus h minus f of a by h. In this sense, basically, we just need to figure out what is the function and find the limit for it. Let's look at an example for it to make more sense. Consider the question that says, find the equation for the tangent line to the hyperbola y is equal to 3 by x at the point 3, 1. Now, when it comes to the limit definition of derivative, ask yourselves two questions. What is the function here? What is f of x? In this case, f of x is 3 by x. And what is a here? As they have given, a is the input that a function will be taking. Now, most likely, a would be the only value given in the function. In this case, it's 3, 1. And as you can see, we are just taking x values. So here we will be taking the value 3. Now, we'll plug these two infos in the formulas and solve it. So this will look like following, where I replace them. I have first put the input values of 3 everywhere, and then I'll put the function, which is 3 by x. So instead of x, I'll put the given values 3 plus h in this case, and 3 by 3, which turns to 1 in this case. Now, while it might seem that it doesn't lead to anything, carry out as much simplification as possible. In this case, the 3 and the 3 cancel out, and we end up with a negative h. The negative h and the h cancel out, and then we're left with negative 1 by 3 plus h, which becomes negative 1 by 3, which is also our answer. Another question that would come up would be, in terms of velocity. As it might come forward, the velocity is actually the derivative of distance with reference to time. So in these questions, our f of x in this case would be the value of time, and the function would be the way distance has been explained. When it comes to velocity, most frequently distance has the formula of 4.9 t squared. If you look into physics, 4.9 is technically acceleration due to gravity divided by 2 using the equations of motion. However, for the sake of calculus, we'll just need to put on this formula 4.9 t squared. So in this question, the f of x is 4.9 t squared. And the a here is 5 seconds. I will plug these into the formula and simplify the question. As you can see, this is the first equation, and we'll put in the function form 4.9 a plus h whole square, 4.9 a square. Then we'll simplify it, and finally we get to the conclusion of 9.8 a. So velocity at time a would be equivalent to 9.8 a. After we know this, we can move to the other part of the question, which is velocity after 5 seconds, which would be just using the formula given by the previous part of the question, which is 9.8 a. Instead of a, we would put in 5 seconds, which gives us 49 meters per second. For the second part, how fast is the ball traveling when it hits the ground? How fast refers to velocity. But here they are asking how fast is it traveling when it hits the ground. So we do not know at what point does it hit the ground. What we do know is that 4.9 t square is equal to distance. And the distance as given in the question is 450 meters. Calculating that, we get time is equal to 9.6 seconds. As you will see, when we carry out the square root of t square, the answer is positive, and we are not considering the negative answer because time cannot be negative in this context. Plugging the value of 9.6 into our original function 9.8 a, the value we get here is 94 meters. And that does with the review. An important thing you might want to look into is the sample papers for the review, which would be available on the course websites. At the same time, you can also just Google ASU Math 265 practice paper review, and these questions would turn up. You can try solving the questions. If you have doubts, you can come to the tutoring center or ask your professors or TAs, and that should have you ready for the first exam. Have a good day.